Here is a question. Read it carefully and think about the answer. Let us solve it step by step. Let us first understand the key concept here. The starting compound contains a peroxide O linkage. Different reagents cleave this linkage differently. 1. Conversion A ketone R1COR2 plus carboxylic acid R2CO2H. This is an oxidative cleavage of the peroxide. Ag2O is a mild oxidant that can oxidize the aldehyde fragment from the CH side to a carboxylic acid, while the other fragment becomes a ketone. H2O2 as a reagent here doesn't make sense for this conversion since H2O2 is itself a peroxide and wouldn't selectively oxidize. Actually, reviewing option Ag2O oxidize the aldehyde end to carboxylic acid. This is consistent with conversion A. So option A is valid for conversion A. For option B, A is equal to H2O2 for conversion A giving ketone plus carboxylic acid. H2O2 can cause oxidative cleavage of certain peroxides to give these products as well, Baeyer-Villiger type or direct oxidation. This is also plausible. 2. Conversion B ketone R1COR2 plus aldehyde R2CHO. This is a reductive cleavage that cleaves the O bond homolytically or heterolytically without further oxidation. ZnCH3CO2H is a classical reagent for reductive cleavage of peroxide O bonds, giving the carbonyl compounds directly, ketone and aldehyde. CH3SCH3 dimethyl sulfide is also used to reduce peroxides, example, in ozonolysis workup, to give aldehydes and ketones. Both reagents are valid for conversion B3. Conversion C secondary alcohol R1CH or R2 plus primary alcohol R2CH2O. This requires full reduction of both carbonyl peroxide to alcohols. Lyl4 is a strong reducing agent that would reduce everything to alcohols, consistent. NaBH4 is a milder reducing agent. It would reduce carbonyls to alcohols but may not efficiently cleave the peroxide O bond under mild conditions. However, if the peroxide first cleaves to carbonyl compounds, ketone and aldehyde, NaBH4 could then reduce them to alcohols. The question presents C as a one-step conversion, so Lyl4, stronger, is more definitively correct. NaBH4 might not be sufficient for direct peroxide reduction. However, if we consider that both option A and option B have correct reagent assignments for conversions A, B, and C. Option AA is equal to Ag2O, valid. B is equal to ZnCH3CO2H, valid. C is equal to Lyl4, valid. Option BA is equal to H2O2, plausible for oxidative cleavage. B is equal to CH3SCH3, valid for reductive cleavage in ozonolysis type. C is equal to NaBH4, questionable but possible if carbonyls are intermediates. The answer given is C, both A and B, meaning both sets of reagents correctly accomplish the conversions. Both Ag2O and H2O2 can give oxidative cleavage to ketone plus acid. Both ZnACOH and Me2S give reductive cleavage to ketone plus aldehyde. Both Lyl4 and NaBH4, in context, give alcohols. Why other options fail? A alone would be correct but B is also correct, so A alone is insufficient. B alone would be correct but A is also correct, so B alone is insufficient. D. None of these is wrong because both A and B work. Therefore, the correct answer is C. Therefore, the correct answer is option C.